Okay, so what do we actually consider to be division? All right, so we're going to define a couple of things. So let's start off with A over B and C over D and E over F. We're going to make those all elements of the rational numbers. Okay, sorry, F there. And we're going to say that A over B divided by C over D is equal to E over F if and only if C over D times E over F equals A over B. Okay, so what is this? This is actually the same definition that we've used before for division. So we say that when we divide numbers, that's like unto the result we get from the division problem is converting into a multiplication problem. In other words, it only is true that if I divide two things together, I get an answer. If I take that answer and multiply it by one of the things, then I get the other thing. Okay. In other words, we convert division into multiplication and think about it with multiplication rules because we have lots and lots of those. This was like unto, well, let's see. So let me kind of go back to this A over B divided by C over D then. I don't want to write C over D, do I? All right, so C over D. That's where we all learned the rule, if you divide by a fraction, you multiply by its reciprocal. Okay, that's what that's referring to. Let me put some numbers in here so for those that are variable phobic, get a sense of what I'm talking about. So let's do 2/3 divided by 3/8. Okay, so that's our old classic rule of multiply by the reciprocal of the second fraction. So 2/3 divided by 3/8 is the same as 2/3 times 8/3. So that's 16 over 9, which we can go into 1 and 7/9. Wow, would be our answer for that. Okay, so a lot of our earlier techniques for estimation and doing mental math still work here. Let me give us a couple examples to work with. We're gonna, again, it's kind of weird. I'm trying to explain to you how to do this in your head, so you really shouldn't be writing it down, although I would write it down so you can see how the form works. So 12 times 25 times a fourth. Let's do 5 and a sixth times 12. And let's do 4/5 times 20. So I'm going to kind of talk you through each of those three approaches. So one of our mental techniques is I can rearrange the order that I multiply using the associative property of multiplication. So I'm going to pick to multiply 12 times a fourth first. And then 12 times a fourth, well, that's 12/4 or 3. And then 3 times 25 is 75. So that would be something that we could do in our heads to come up with our final answer. Okay. This next one, 5 and a sixth, I'm going to rewrite it using the distributive property. And then I'm going to distribute the 12 in. So in my head, I'd be thinking 5 times 12 plus 12 times the sixth. Well, 5 times 12, that's 60. And then 12 times the sixth is 12 over 6, so that's 2. So I'd get an answer of 62. All right, and the last one here, 4/5 times 20. Again, in my head, I would think, well, let me take care of the fifth first. So I'd make that be 4 times 20 divided by 5. And then 20 over 5 is just another 4. So we get 16. But those would all be things that we'd be doing in our heads to generate our answer. All right, let's talk about estimation skills. And some of the estimation skills that we covered in the previous section can still apply here. Again, we're not looking for exact answers. We're just looking for a roundabout answer to what we would expect it to be. So I'd look at my two numbers, and 3 1/4 is kind of close to 3, and 7 8/9 is kind of close to 8. So I would expect this to be likened to the product of 3 times 8, which is 24. And if I want to get a north estimate, if I want to get a higher estimate, then I do 4 times 8, which is 32. So the answer itself should be somewhere between 24 and 32, closer to 24. As far as the division goes, okay, so 24 and 5/7. Want to think of something compatible to that. So I know 24 rounds up to 25, but looking at the 4 1/8, I know that thing's pretty close to 4. So I'm going to round down for this one. Again, this is okay to do because I'm estimating. So really, 24 divided by 4, that would be 6. So I know 6 is kind of close to where I would expect to be. Now if I want to go the other direction, where I see 24 and 5/7 actually rounds up to 25, and compatible with 25 would be 5 here, I get an estimate of 5. So I know the answer's got to be around 5 or 6 as far as estimation goes. Okay, so I want to remind us of a couple of the exponent rules, and then we'll look at some illustrations of this. So if I am multiplying two things with the same base, I'm going to add the exponents. If I am dividing two things with the same base, I'm going to subtract the exponents. If I am raising it, a to the m raised to the n power, so if I'm raising an exponent to an exponent, now I'm going to multiply. Try to make that look like the letter A. If I have a fraction raised to an exponent, I can distribute the exponent into each component of the fraction. If I have a negative exponent, I can rewrite that as the reciprocal, and then I can distribute that to each component of the fraction. So all of those are equivalent to each other. If I have something to a negative exponent, I can make that be a positive exponent by putting it in the denominator of a fraction. And if I have anything to the 0th power, that is equivalent to 1. Alright, so let's take a look at some expressions that utilize some of these exponent rules. Let me start with something like a plus b to the negative 1 power. And I want to compare that to a to the negative 1 plus b to the negative 1. Hopefully get us to recognize something. Alright, so what is this first one? Well, in order to make the exponent positive, I want to put that in the denominator of a fraction. And over here, same thing, 1 over a plus 1 over b. Now I'm going to go one step further because we can add these together using our fraction rules. So this would be b times 1 plus 1 times a over ab. And so this would simplify down to b plus a over ab. Now I want to point something out. those are not the same expression. Those clearly are not the same, okay? Which means those original statement are not equivalent either. And yet, I see as a teacher in the classroom, I see students make that misunderstanding all the time as far as exponent rules go. So I think it's good if we expose students to that sort of thinking now and make sure that they don't make those sort of mistakes later on down the road.